Jai Hind to all of you. I am Dr. Ritish Kumar. I am going to present the lecture on the topic of magic tea and directional coupler. So, which lie in the subject of microwave and radar engineering. So, let's begin the topic with the magic tea. So, first we need to understand what kind of magic tea we have in the lab. So it is a combination of E plane tea and H plane tea as well, we can say. So also we can say it is a hybrid of E plane tea and H plane tea as well. So this is a the first one is the E plane tea and second one figure is the H plane tea. What is the basic difference in between these two tea? As we can clearly see here, if I remove this part auxiliary, we can if I remove this part in the figure, then we can say this is a kind of simple waveguide. So so in this figure we can say this is a main arm and this one is the auxiliary arm, we can say this one is auxiliary arm, and here you can see this one is the main arm and this one is the auxiliary arm, right. So you can see the orientation of electric field in the main waveguide in the both plane T. So in the main waveguide you can clearly observe here the field distribution in the main waveguide in the upward direction or downward direction, right. So here we are talking about the fundamental TE10 mode here. So TE10 mode is looking like in similar trend, that is looking like this way, high, sorry, that is low, this should be low, high and low. So here this is a boundary condition we have, this is the one boundary condition and this one is the second boundary condition and this one is the third boundary condition here. So you can see here the field is going upward direction, right, and here the field is going in the downward direction. So we can say here here the tail of the arrow is lying in this boundary and here the arrow is lying to above this boundary, right. So you can clearly see here the field comes towards from this port, it looks like in this way, and throughout this boundary the tail of the arrow comes into the picture, and throughout this boundary the arrow of the head of the arrow is comes into the picture. So here similarly you can see here this is a one boundary condition and this is second and this one is the third. If you look in the electric field distribution in this figure, so you can clearly observe here the field goes upward direction. So arrow the head of the arrow comes into the picture in this boundary as well and in this boundary also. So if I talk in terms of plane, so actually the field lie in this plane. So this plane is known as E plane and perpendicular of this plane is known as H plane. As we know the right hand rule, the E plane and H plane both are perpendicular by nature, and if both are perpendicular we have a propagation direction perpendicular to both of the plane. So if I say if the electric field in the bidirection and magnetic would be in the x direction, then we have the direction of flow is in the z direction. This is the concept of right hand thumb rule we have. So in terms of plane we can say if the auxiliary arm lie parallelly in the plane of E, then we can say this this kind of T junction is known as E plane T. In other terms we can say if if this auxiliary arm lie perpendicular to the H plane, then we can also say this kind of plane is the E plane T. Both plane T are both E and H plane T are complementary by nature. So we can see here if the this T lie parallel to the H plane, if this plane is parallel to the H plane, then we can say this is a kind of H plane T. In other words, we can say if the auxiliary arm lies perpendicular to the E plane, then we can say this one is the H plane T. So here you can clearly see here that I already explained the terms. So if I say this one is a port 1 P1 and this one is a port 2 and this one is the port 3, right. So if I talk, if I apply the input signal in the input signal at port 1 and port 2 simultaneously, and it has the opposite in phase, that is both are 180-degree phase shift with each other, then we have the output. What should be the output at port number 3 in that condition? If we have in the same opposite phase input apply at the port 1 and port 2, then we have the addition of the power at port 1 number at port number 2 and port number 3. Suppose P3 should be equal to P1 plus P2 in the condition of if the phase in phase opposition. If I say in terms of same phase, if I apply the same phase at port number 1 and port number 2, then we have the output at port number 3 would be in P1 minus P2 in the case of phase, in the case of same phase, right. Similarly, so we can say in terms of opposite phase, it act as a, in the phase opposition it act as a adder, and in the case of same phase it act as a subtractor port, adder port and subtractor port. Whatever we have observed in the case of E plane, just we have the opposite in the case of H plane. So if I say if we apply the input at port number 1 and port number 2 in the phase opposition, then we have the power in at port number 2 would be P1 minus P1 plus P1 minus P2, phase opposition P1 minus P2, and in the phase, in the same phase it would be P1 plus P2. Whatever we have observed in the case of E plane T. So at last we can conclude the E plane T and S plane T both are complementary by nature. If I apply the same phase, it will work as a subtractor, and if I apply the phase opposition, it will work as a adder respectively. So next we can explain it in further in detail. So you can clearly see here at the port number 1 you can see both are in opposite in phase. If you apply the input at port number 1, right, so output you will get the output at port number 3 and port number 2, and it will you will have in the orientation like in this way, right. So you can clearly observe here. So if you apply the input at port number 3, so the output you will get at port number 1 and port number 2, and you can see here the both are in the opposite in phase with each other, right. So this is a 3D diagram of the E plane T. You can see this is the E plane, this is the direction of electric field, and this auxiliary arm lie parallel to the E plane. So that's why we call this is a E plane T, right. So and the scattering parameter for the E plane T is, you have to remember this scattering parameter of the E plane T. So you can clearly see here what should be the significance of 1 by root 2. You can see here this one is S11, S12 and S13 for this, yeah, right. So you can, and this one is S21, S22 and S23. You can clearly see S13 is equal to minus S23. So you can clearly see here this one is the input port and this one is the output port. So you are applying the input at port number 3 and receive the input at output at port number 1. Here you are applying the input at port number 3 and receiving the output at the port number 2. So both are in the equivalent magnitude, but it has the phase opposition, right. So 1 by root 2 also gives also represents the, it is a half power divider. It works as a half power divider if you apply the input at port number 3. So I think this scattering matter is clear to all of you. Next is the H plane T. You can clearly see here this is a main arm, as we have already discussed in the last slide, last slide. This one is the main arm and this one is the side arm, right. If you correlate this, if you compare this figure to this 3D structure, so this side arm is perpendicular to this side arm. So you can see this is a E plane and this one is the H plane. So we can say this auxiliary arm is perpendicular to the E plane while it is parallel to the H plane. So that's why we call this plane T is a H plane T, right, because this side arm lies in the H plane, right. So if you apply the input at port number 1, you will get the output at port number 1. If you apply the input at port number 3, you will get the output at port number 1 and port number 2 simultaneously, right. So you can clearly see here the direction of E field is in the upward direction and you will receive the power in the same phase, right, at the same phase at the both ports in the upward direction. So this is the working phenomena of H plane T, and we can say this one is if you apply the power at port number 2, it will divide the power equally in port number 1 and port number 2. You can clearly see here if you compare this S13 and S23, both are equal in magnitude and in phase as well, right. And under root 2, 1 by root 2 is the half power point as well, half power point as well, right. So we can say E and H plane T is the are the power dividers if you apply the power at the auxiliary arm, right. Now comes to the magic T. We will discuss what is the magic T. Magic T is nothing but the combination of E plane T and H plane T as well. So also we can say this is a hybrid T because it is a combination of E plane T and H plane T. So this part we had already discussed in the last slide, and this part is we have already discussed in the previous slide. So you can see this is a E arm because it lies in the E plane T, and this is a H arm because it lies parallel to the H plane H plane, right? That's why we call this ER and this one is the HR. As we already discussed that if you apply the input at port number 1 and port number 2 in the same phase, suppose in the same phase, if you apply same phase, then you will get, suppose if I draw in the dotted line, right, same phase, then you will get the output in the opposite phase at port number 2 3, and at port number 3 it will lie in the same phase, right? I hope this one is clear to all of you. And so because both are in the opposite phase, you are getting, that's why it will act, it will cancel out it will cancel out with each other. That's why it works as a subtractor port that I represent with the delta. And because at the port number 4, that is H plane port, so you will get in the same phase. That's why this port it acts as a adder port or summer port. So at a time both ports can be act at a time. One port will act as a subtractor port and another port will act as a adder port, right? In the case of if you apply the same phase input at the port number 1 and port number 2, if you apply the input at port number 2 in the opposite phase, suppose this one, then this port will convert into the subtractor port, convert into the adder port, and adder port is converted into the subtractor port, right? So delta means subtractor port when you apply the opposite, when you apply the input at the, when you apply the input at the same phase, right? Adder in the opposite phase, and for this when apply input in the same phase and opposite phase, right? So you can clearly observe here that we have I have written here clearly all the points is clear to all of you, and you can see here these E arm and H arm both are perpendicular by nature, and E field also perpendicular with the H field. That's why both are cross coupled with each other. If you apply the input at port number 3, you will not get anything at the port number 4. Similarly, if you apply the input at port number 4, you will nothing, you will nothing get at the port number 3. So we can say port number 3 and port number 4 both are isolated by nature. And why we isolated by nature? So why we call this kind of junction is a magic T junction? Because if you the first point is, if you match two port, if you match two ports, suppose if I match port number 1 and port numbers 2 with each other, then you will get the automatically match port number 3 and port number 4. That is the magic of this, that is the magic of this hybrid T or EH plane T. So that's why we call magic T, right? So this is the condition of isolated port. I think this magic T concept is clear to all of you. Now comes to the scattering parameter of this magic T. This is a scattering parameters, scattering matrix of this magic T. Because this is a 4-port device, so that's why we make 4 cross 4 scattering matrix here. So you can clearly observe here, this is the matching condition, because this is nothing but S11, S22, S33 and S44. These all are the reflection coefficient. Reflection coefficient. So reflection coefficient, here you are getting the 0 value, that's why there is no reflection, that's why we can say all port are in the matched condition. That's why we call this is a magic T. If you make it 2 port in the matched condition, you will get other 2 port in the matched condition as well. So this is a scattering matrix, and you can clearly see, we know that E and H plane T are the will work as a half power divider. That's why here you will, here S13 is having the value of 1 by root 2, and yeah, this one is S13, and S23 also will, we can say this one value is also 1 by root 2. This is a half power point value, right? So that's why we call this a half power divider as well. So I think this magic T is clear to all of you. I can summarize the magic T. So you need to remember 2 or 3 points here. Magic T is a kind of hybrid T. This is a combination of E and H plane T. And what is the magic in the magic T? If you match if you match the 2 port of the magic T, if P1 and P2, and you will automatically match other 2, you will get the other 2 ports in the matched condition as well. So this is the condition of, this is the magic of magic T. Now the next device is a directional coupler. So directional coupler again is a 4 port device, right? Port 1, port 2, port 3 and port 4. This is a general directional coupler. So you can see here, we are saying the port 1 is the input port, and port 2 is the throw port, port 3 is the coupled port, and port 4 is the isolated port. So we can say this is a combination of 2 waveguides. This is a one waveguide, we can say this one is the another waveguide. So we can say this is a primary waveguide, this one is the secondary waveguide, right? So coupling always be having in the other waveguide. If you apply the input at port number 1, you will get the power at port number 2, 3 and 4 respectively, while the coupling always be occurring in port number 1 and port number 3, and port number 2 you will get the throw power, and port number 4 is the isolated port. Why we call this is isolated port, coupling port and throw port, we will learn in the 2 port coupler in the next slide. So related to this directional coupler, we have some coefficient of factor there we have mentioned here. The coupling factor, second one is the directivity factor, isolation factor, isolation loss, and the insertion loss as well. So coupling always be happening in between port number 1 and port number 3. So here you need to remember, here we are talking in terms of power, that's why we are taking the log in terms 10 log in terms multiplication with 10. If you right, so this is a ratio in between port number 1 and port number 3, then you will get the coupling coefficient. If I talk in the directivity, so directivity, if you correlate this thing with the antenna radiation pattern, so in the antenna radiation pattern, what will be the directivity is nothing but the ratio of front power to the back power. So if you apply the input at port number 1, simultaneously you will get the power at port number 3 and port number 4 respectively, and this power is, we are saying this is forward power and this one is the backward power. That's why we need to take the ratio of port number 3 and port number 4 respectively. So here directivity is the ratio of P3 by P4, and the isolation is the ratio of port number 1 and port number 4, and we can see here P1 by P4, and insertion loss is in between the port number 1 and port number 2, that is tan log P1 by P2. So this is the some kind of factors we need to remember for the directional coupler devices, right? So what is the construction of 2-hole directional coupler? Why we call port number 4 here is the isolated port, and port number 3 is the coupled port. Isolated means there, if I apply the input at port number 1, we are nothing getting at the port number 4. So this is the construction point, construction of two-hole directional coupler here. So you can see this is a primary waveguide and this one is the secondary waveguide, and in between these two there are two holes are given into the picture and given into the construction of the two-hole directional coupler. And this distance is need to understand why we take this distance for a two-hole directional coupler. This is a very important point to design a two-hole directional coupler. So here you can see that if two odd multiples of 2 lambda z by 4, if you make it n is equal to 0, so it comes L is equal to lambda z by 4. So you can say the distance between these two holes are quarter wavelength at a particular frequency, right? So what should be the logic? So if you apply the input at port number 1, then you will get the power at port number 2, port number 3 and port number 4 simultaneously, right? So suppose I consider the received power at port number 4. How you can get the power at port number 4? So there are two ways to travel this path. The first path is this one, right, and second path is this one, right? So we need to understand the path difference or phase difference. So what is the relation between path difference and phase difference? You here phase difference is equal to 2 pi by lambda z into path difference, right? So you need to understand what kind of path difference or phase difference you will get at port number 4. So you can see the travel path distance in from hole number 1 and hole number 2 are equal. That's why the phase difference is 0. That's why both power received at port 4, hole number 1 and hole number 2 are in phase. That's why the power becomes added at port number 4, right? That's why we will get the power at port number 4. Now what would be the condition to receive the power at port number 3? You can see here there are two paths to receive the power at port number 3 from port number 1 is, this is the first path and this one is the second path, right? So how much path difference you will get into the at the port number 3? So you can see this one is the lambda z by 4 and this one is the lambda z by 4 again. How much path difference in between path 1 and path 2? That would be total path difference is equal to lambda z by 4 plus lambda z by 4. That would become lambda z by 2. If you if you find the phase difference, then you will get 2 pi by lambda z and lambda z by 2. So it would become pi. So you can say both power received at port number 3 are out of phase. That's why both will cancel out with each other. That's why you are the power would become 0 at port number 3. That's why we call P3 is an isolated port from P1 and you will get the power at port number 4 here, right? And port number 2 is a throw port. Whatever you will give the input at port number, you will receive at port number 2, right? So this is a functionality of two-hole directional coupler, how it works. So this is the main point you have to remember, that is lambda z by 4. I hope this one is clear to all of you, and this is the scattering parameter of this two-hole directional coupler. you need to remember of this scattering parameter of two-hole directional coupler as well. So I think these two devices is clear to all of you, that is two-hole directional coupler and magic tee as well.